discuss carrier concentration and Fermi level. Given a carrier concentration or a current through the device, you can calculate the carrier concentration, and knowing the carrier concentration, it is possible to calculate the Fermi energy. This is required in several design characteristics. So we will discuss the relation between this. But before I start with the lecture, let me just discuss the quiz which we had taken in the last class. That is quiz 2. Define rho of k, the density of states, and what is the unit of rho of k. The answer is rho of k is defined through rho of k dk. Rho of k dk gives the number of states. Rho of k dk gives the number of states between k and k plus dk per unit volume. You can see your notebook, we have written this definition many times. Or if it was rho of E, you would have written rho of E dE is the number of states between energy E and E plus dE per unit volume of the material. If you write the correct definition, then part B, that is to determine the unit, part B, which is to determine the unit, rho of k dk is the number per unit volume. Therefore, its dimension is meter minus 3, or per cc is the unit. Therefore, rho of k has units of meter cube by dk. Dk, the dimension of k is 2 pi by lambda, which means it is length inverse, so meter inverse, and therefore the correct unit of rho of k is per meter square. Exactly, you can see what is the unit of rho of E. Rho of E will be number per unit volume per unit energy. That will be the unit of rho of E. Today we recall what we had seen in the last class. The carrier concentration N is given by N of E dE, which is equal to rho. If it is N, it corresponds to carrier concentration of electron, which means the conduction band. So rho C of E into F of E, the probability of occupation dE. Similarly, if you are calculating the carrier concentration of holes in the valence band, then this is equal to P of E dE, which is equal to rho V of E F of E dE. It is interesting to see what will be the integrand, and it's integrated over the limits of energy. So if it is conduction band, then EC to infinity, and if it is valence band, it is infinity to minus infinity to, or minus infinity to EV, from somewhere from below to EV. The integrand here, so let us have a graphical representation. See the graphical representation. It gives you graphical representation of the carrier density, So N of E here is the integrand, which is equal to rho C of E into F of E. How does it look like? It's a product of two functions. This is the energy axis, rho C of E, so if this is EC and this is EV, then rho C of E varies like this and rho V of E varies like this. So along the x-axis we have rho C of and rho V. So this is the lower one is rho V and this is rho C. On the same graph, this is a product of two functions. In the same graph, I want to plot also f of e. So if this is 1, this is 0, f of e, then f of e, if I take for example an intrinsic semiconductor, then EF remains somewhere in between, somewhere near midway between EC and EV, and therefore the density, if I plot f of E, it would look something like this. I should probably have brought a color chalk, but anyway, I suppose you follow this. This is f of E. So wherever you have 0.5, so this is EF. For an intrinsic semiconductor, EF remains somewhere in between, somewhere near midway. So for E greater than EC, for every value of E here, the integrand is product of this function and this function, f of E multiplied by rho of E. F of E is maximum near EC and it goes down to 0, almost 0, as E increases. This of course increases as square root of E. So how would the product look like? Here it is 0, therefore if you find out the product of these two, it would vary something like this. It will initially increase and then it will come down. So this third variation that I have plotted is n of E. This third variation is the product of this and this, which means for every given value of E, multiply f of E by rho of E, you get this value. So it goes up to a maximum but then starts decreasing because f of E is decreasing. That is n of E. Integrate over E, which means area under this curve gives you n. So the carrier density, the carrier concentration is area under this curve because we have integrated over E, dE integrating. Similarly, if you see here, for the valence band, this is the density of states, and in, yes, I made a small mistake, please correct this. Because the probability of occupation is 1 minus f of E. You can point out it earlier if you, so 1 minus f of E. Again, you see 1 minus f of E is this part because from here to here it is f of E and this small length here, magnitude, corresponds to 1 minus f of E. That is very large near EV but decreases down to 0. The density of state is 0 at EV and continuously increases. So if you take a product of these two, here also you will get a curve which goes up to a maximum and comes down. And area under this curve, you are integrating over E, area under this curve gives you the carrier concentration P. Area here gives N, this is N. Integrated, the curve is N of E, but the area The curve is of course N of E, but the area under that gives you P. Let me quickly go to how did it look like in the case of N type and P type. You see that these areas are equal. In an intrinsic semiconductor, the area under this curve here will be equal to the area because N is equal to P. If you use a doped semiconductor, so let me draw at the same scale, almost near the same height. So this is EV, EC, but this time the Fermi level in the case of N-type semiconductor is somewhere here. The Fermi level is up. This is now for N-type I am plotting EF. The density of states varies the same way, is the same material but now N-doped. Fermi level is up, which means the probability F of E is half here at this value, it's half, which means the curve would look like this. And the density of states here is F of E. Please see the F of E curve has been shifted. Look at this. Compared to this, it is shifted up because EF is up. Therefore, what do you expect now? The product of this into this quantity is now large compared to this. You see the magnitude here is very small. Here the magnitude is large because the curve has shifted up. F of E curve has shifted up. So in this case, you will see if you take a graphical represent, if you take a product, it will look something like this. Whereas in the second case, you see that magnitude 1 minus F of E is very small. Although the density of states increases, but that is very small. And therefore, if you, this will come out to be very small. And therefore, the area under the curves clearly tells you that in an N-type semiconductor, N is much larger compared to P. So this is for N-type. This is graphical representation. Qualitative, of course. Qualitatively I am drawing, but if you can indeed multiply the two functions and see, you will get this kind of variation. And if you go for the P-type, so first draw the density of states, and P-type. So Fermi level is now below. So this is EC, EV. Fermi level is below, which means if probability 1, 0, so half is here. Which means the curve is now so this is my F of E now. And you see that the magnitude 1 minus F of E that you see here, 1 minus F of E is much larger compared to the 1 minus F of E that you saw here. At the same energy value, if you go here, the 1 minus F of E, because F of E itself appears to be about 0.99 or so. So 1 minus F of E is the difference, very small, but here now 1 minus F of E is large. Whereas here F of E is very small. Please remember F of E is now along the x-axis, which means this distance gives you F of E. This magnitude of the length is proportional to F of E. So here F of E is now very small. Density of states is the same because that does not depend on the doping concentration or very little dependence. It depends on the material only. And therefore, if you take the product, this time you will get N of E varying like this, whereas P of E varies. And the area under the curves, give you P and so you can clearly see from this graphical illustration also that what we have plotted is carrier density versus E, and the area under N of E and P of E tells you the total carrier concentration. So this is for the p-type semiconductor. Is that all right? So we have also derived a mathematical expression for P and N. Under the Boltzmann approximation, we have P is equal to NV into e to the power E minus EV minus EF, EV minus EF by KT, and N is equal to NC into e to the power EF minus EC by KT. These are under the Boltzmann approximation, where NV is 2 into mv kT by 2 pi h cross square to the power 3 by 2. All of them are constant except mv, that is effective mass of holes in the valence band, and Nc is equal to 2 into mc kT by 2 pi h cross square to the power 3 by 2. This is under Boltzmann approximation, and we have discussed Boltzmann approximation, which simply says that if EF minus EC is much greater than KT, that is when the Fermi level lies well within the band gap, then you can use Boltzmann approximation. So under Boltzmann approximation, N into P therefore is equal to Nc into Nv into N into P, Nc into Nv into EF, there is 1 plus EF, 1 minus EF, so we have e to the power minus EC and EV, so it is minus EG by KT. N into P is equal to Nc into Nv minus Eg by KT. For an intrinsic semiconductor, N is equal to P is equal to Ni. And if you substitute here, Ni square is equal to Nc into Nv e to the power minus Eg by KT. Please see that this expression is independent of EF. This expression is the same as this expression. It's independent of EF. Therefore, whether you take an intrinsic material or an N-type material or a P-type material, the right-hand side is the same. It means that N into P is equal to Ni square for all semiconductors. under Boltzmann approximation. The clause always remains, but n into p is equal to ni square. This is sometimes called the law of mass action. Np is equal to ni square. Therefore, the carrier concentration Ni, the intrinsic carrier concentration Ni is Nc into Nv to the power half into e to the power minus Eg by kT. Please see the by 2 kT. I am sorry. By 2 kT. Eg by minus Eg by 2 kT. Expression for Nc and Nv are here. Therefore, given a material, if you know the effective mass of holes and effective mass of electrons, rest of them are all constants, you can calculate Nc, Nv, and therefore the intrinsic carrier concentration simply depends on the band gap Eg. Please put some numbers. Let me, for example, calculate Nc. What is Nc? Nc is equal to, let us take for example gallium arsenide. Nc is equal to 2 into Mc, that is effective mass of electrons at 300 K is 0.067 into M0 into 9.1 into 10 to the power of minus 31 kg Mc multiplied by Kt 1.38, that is K, Boltzmann constant. K is 1.38 into 10 to the power of minus 23, T 300 K divided by 2 into pi into H cross 1.05 into 10 to the power of minus 34 square and whole to the power 3 by 2. So this will come out. I'll give you some values that I have calculated. This comes out to be 4.74 into 10 to the power of 23 per meter cube. Because all these are SI units, therefore this came out per meter cube, or 4.74 into 10 to the power of 17 per cc. Nc. Similarly, you can calculate Nv, and I want to give you these numbers. Some numbers I have calculated, so let me give you typical numbers. Okay, all of it is visible. So typical values of Nc, Nv, Ni per cc. This is the material silicon, band gap is 1.1 eV, and you can see Nc, Nv and Ni calculated by taking constants. So it is advisable to take some constants from books or literature and calculate these Nc, Nv and Ni. This is indium phosphide. I have written for 3 very important substrates for optoelectronics. The most important substrates are gallium arsenide and indium phosphide. So indium phosphide has a band gap of 1.35 eV, and you can see the important point to see is for smaller Eg, as you have seen in this expression for Ni, it depends on Eg. Ni is equal to Nc into Nv to the power half. So smaller the Eg, larger will be the carrier concentration Ni. And as the band gap increases, you can see that the intrinsic carrier concentration decreases. If you take gallium nitride wide band gap semiconductor, which has a band gap of 3.4 electron volt, the intrinsic carrier concentration is 10 power minus 10. It is of the order of 10 power minus 10. So a strong dependence on the band gap. So it's an exponential dependence. And of course, it has a temperature dependence. These numbers are calculated at 300 K. So please calculate and see whether you get such numbers. For an intrinsic semiconductor, N is equal to P, which implies Nc into e to the power Ef minus Ec by Kt is equal to Nv into e to the power Ev minus Ef by Kt. What is different in Nv and Nc? Only this is the difference, effective mass. The rest of them is the same. Therefore, this means m to the power 3 by 2, mc to the power 3 by 2 into e to the power Ef minus Ec, simple algebra, by Kt is equal to mv to the power 3 by 2 e to the power Ev minus Ef by Kt. I can bring that Ef here, so I have e to the power twice Ef by Kt is equal to mv by mc to the power 3 by 2 mv by mc to the power 3 by 2 into e to the power, what do we have? This Ef I have brought here, Ec goes there, so it is e to the power Eg by Kt. Ec plus Ev, Ec plus Ev by Kt. Is that all right? Okay. Therefore, Ef, we can simplify this. So, take ln on both sides. So, you have 2 Ef by Kt is equal to ln 3 by 2 ln mv by mc plus Ec plus Ev by Kt. Or multiply by Kt on both the sides and take this to the other side. So, you have EFI. For intrinsic semiconductor, I was writing this expression. So, I standing for EFI is equal to Ec plus Ev by 2 plus 3 by 4 Kt ln mv by mc. The expression for Fermi level of a intrinsic semiconductor. You can see that it is exactly in between Ec plus Ev by 2 plus a term here. only when mv is equal to mc, ln1 is 0, therefore the Fermi level will lie exactly midway between EC and EV if the effective mass of hole is equal to effective mass of electrons. Otherwise, there will be a small difference here. Now, how small is the difference? The difference is really small because you can put the corresponding values for MV and MC, and you can see that this difference is going to be very small. For example, if this comes out to be a factor of 10, if you take gallium arsenide, MV is 0.45 and 0.067, this is approximately 8. So if I take 10, ln 10 is how much? Ln 10 is 1 divided by 2.303, which is 0.4, approximately 0.4. So this term is approximately 0.4 multiplied by, so there is a 3 by 4 here, approximately estimating what is this, what is the typical number here, 3 by 4 into kT is approximately 0.025. So the number is really very small. So this is 10 times and this is 0.075 divided by 10, which is equal to 0.0075 EV. Approximately estimated, just to find what is the order. So what is the point? Even if MV and MC are very different, as in the case of practical materials, the second term is very small, and therefore with some approximation we can say that the Fermi level for an intrinsic material lies midway between EC and EV. It's not exactly, but almost midway between EC and EV, because EFI is equal to EC plus EV by 2. What about the Fermi level of other materials, that is p-doped and n-doped? We had an expression for carrier concentration, N is equal to Nc into e to the power EF minus EC by KT. We have written this expression already. P is equal to Nv e to the power EV minus EF by KT. I want to find out EF from here, so you can bring this here, take log, and you get EF. So this gives you EF is equal to EC plus KT into ln n divided by Nc. N by Nc, then take ln, so this will come down, multiply by KT, you will be left with EF minus EC, take EC to the other side, so you have got expression for EF. From this expression you get here EF is equal to EV minus KT into ln P divided by NV. You must be wondering, Fermi energy EF, EC plus this, which means greater than EC. Is that true? That's not, because this N is much smaller compared to NC. That is why I gave you these numbers. NC is much larger compared to N, and therefore this is a fraction. Log of a fraction is a negative number, and therefore the second term here is negative. So actually it is EC minus something, and therefore it lies within the band gap. So this is under Boltzmann approximation, therefore EF has to lie within the band gap, otherwise these expressions are not valid. If Boltzmann approximation is not satisfied, this is fine for lightly doped materials, where Boltzmann approximation was a good approximation. If Boltzmann approximation is not satisfied, what do we do? Carrier concentration and Fermi level, which means if you know the carrier concentration, NC is known for the given material, KT, EC. So if you know the carrier concentration, you can determine Fermi level. What was the carrier concentration in the case of without any Boltzmann approximation? This was through Fermi half integrals. So Fermi half integrals, there was some constant m, some constant. You can see what is the constant, 1 by 2 pi square into 2 mc kt by h cross square to the power 3 by 2 into the Fermi half integral, f half of eta f. This is that constant which is outside. And what is eta f? Eta f is EF minus EC divided by KT. And recall what we had done in the last class. We had plotted eta f here versus the Fermi half integral f of half of eta f. If you know the carrier concentration, it means you know the value of this Fermi half integral. That is, you know the value here. I just showed a qualitative variation like this. So you know the value of f half of Fermi half integral of eta f. That means if you know that value here, then you can find out what is eta f, the value eta f corresponding to this. So n is equal to, therefore n corresponding to this n, I know this value, and therefore we know eta f. So once you know eta f we know, and therefore EF is equal to EC plus KT into eta f. KT into eta f. Because eta f has been numerically obtained from this graph, because you have found out this for a given carrier concentration, you know this, and from this numerical plot you know what is eta f, and if you know the value of eta f, then you can find out what is the Fermi energy. This is the way to exactly get the Fermi energy without any approximation, no Boltzmann approximation. And this is important because in optoelectronics we will see that most of the devices are degenerate semiconductors, or the Fermi level is entering either conduction band or valence band. Or both the bands. How is that possible? Fermi level entering valence band and conduction band? Yes, it is possible, and that is our next topic. We will see how it enters valence band and conduction band. So EF is equal to EC, EC plus KT in eta f. You can see here eta f value, yesterday I had written eta f values 0, 2, 4, minus 2, 4, 6, minus 6. So this eta f could be positive or negative. Therefore, EF could be greater than EC or less than EC. So it will give you EF value even when the Fermi level enters the band. This is the exact expression where you have to numerically evaluate the Fermi half integral. However, it is sometimes difficult, and there is a very important approximation for, let me not erase this. Very important approximation for the Fermi level. EF is equal to EC plus KT into ln n by n, and that is called the Joyce-Dickson approximation. This approximation you won't find in older books. Joyce-Dickson approximation for the Fermi level. This is a very good approximation. This gives that the Fermi level EF is equal to same expression EC plus KT ln n by n, same term, plus an additional term 1 over root 8 n divided by n. This is an empirical formula, or this is also equal to EV minus KT into ln, because you may be knowing whole concentration P by, this is n by nc, n by nc. Please see the subscript n by nc, and this is nb plus 1 over root 8 into P divided by n. So any of these formula could be used, because in highly p doped material you know P, whereas in highly n doped material you know n. Because when you highly dope, n is nearly equal to the donor ion concentration, that is the doping concentration, because intrinsic concentration is negligible. And similarly, if you highly p dope a material, the P is essentially equal to the acceptor ion concentration. So in some materials you will know P, in some materials you will know n, and you can find out the Fermi level without any Boltzmann approximation. This is a very useful formula. We will need this later when we pass current through the device. For a given carrier concentration, you will have to estimate the Fermi level. The Fermi level will be required, as you will see later on, to, for example, to determine the bandwidth of an amplifier. This is the Joyce-Dickson approximation. For normal calculations, it is sufficient to use this approximation. It may be difficult to get the exact numerical solution of so we know for given carrier concentration how to determine the Fermi level, whether it is highly doped or not. Our next topic will be, so long we have been discussing about Fermi level, the next topic will be Quasi Fermi level. Quasi Fermi level. This is very important, Quasi Fermi level. Normally in electronics, we don't, Quasi Fermi levels are there. Every PN junction, when you operate in the forward bias or reverse bias, you have Quasi Fermi levels in the junction region. There is no more Fermi level, there are Quasi Fermi levels, and it is the difference between the Quasi Fermi levels which will determine the performance of the device. Therefore, we will have to determine Quasi Fermi levels. What are Quasi Fermi levels? Let me just give you a simple idea. In a normal semiconductor, we will discuss this in detail in the next class. However, let me just introduce what is the need to have these Quasi Fermi levels. Why do we need Quasi Fermi levels? If you take our familiar band diagram, let us say valence band and conduction band, the basic picture of valence band. And by this side, so this is EC and this is EV, and by this side, let me also plot the Fermi function. The Fermi function EFC. So this is f of E, and this is 1, 1.0, 0. And this is EC, EV and EC. This is the Fermi function. And where is the Fermi energy? At halfway. So 0.5, go upwards where it intersects, and that is F. If you n-dope this material, this shifts up because there are more number of electrons here, which means the Fermi level will shift up because the probability of finding electrons in the conduction band increases. If you p-dope it, it will shift down. So in n-doped material, you have large concentration of electrons but very little holes, and therefore the shifting was very good because no problem, I shift this up and now I have parallel to this, but you see the probability of having holes is very small, very good. It's the n-type material, very few holes. If you take a p-type material, very large number of holes, so I shift this, the Fermi function is able to describe the occupation probability of electrons in the valence band and the conduction band. Think of a situation where you have very large number of electrons and very large number of holes. What will you do now? The same Fermi function cannot express the probability of finding large number of holes and large number of electrons. Of course, to some extent it is possible because you smear this out further. Please see how did we have Fermi function at temperature T is equal to 0, it was like this. Step function. Temperature increased, this started smearing because there are some electrons and some holes. Temperature increase, this smears more like this. Temperature increase, this can smear further. That is, the probability of finding electron is also larger, hole is also larger. How much can it smear? At best, it can become flat like this, at best, which means it is 50% probability of finding electrons and 50% of probability finding holes. Suppose I have 70% electrons here and 70% holes in both. Can this function? So we cannot describe the probability of finding electrons and holes by one single Fermi function. And then we have to introduce what are called Quasi Fermi levels. We will discuss this in detail in the next class.